Hello and welcome to another video. What I'm going to do in today's video is complete the part of the lecture that was incomplete on complex numbers. So please make sure that you watch the other videos before you watch this video for complex numbers. Um, okay, this was about geometrical interpretation of complex numbers. Not all of them are important. We've already seen how we represent complex numbers as movements. So we've done the coordinate system and all of that. Okay, like in vectors, when you add two complex numbers, you're technically creating a parallelogram. Okay, the more important part is this, and this comes up in a past paper question, and only when it comes up in a past paper question will I be able to tell you all of this. Okay, so please make sure that you take a note of this, that this is important. We can revise that with the recent past paper questions. It says that when you multiply a complex number z by an imaginary number I, the geometrical equivalent to rotating the point representing z by 90 degrees anti-clockwise about the origin. So if you're technically just multiplying by I, you're rotating the point 90 degrees anti-clockwise. Okay, then these are rules for modulus and argument that I will write down again right now here. Okay, but before that I want to show you what modulus and argument are. So I'm going to scroll back quickly and tell you that the modulus of a complex number is the uh, is the distance from the origin. Okay, if you take the complex number to be a point representing the coordinates x comma y, then modulus of z is basically root of x square plus y square, and the argument of a complex number is the angle that it makes with the x-axis. Depends on the quadrants. We've done the rules before, so I'm going to just write down another set of rules for you here, and then we are going to apply it to some questions. So these rules are about, again, modulus and argument, but modulus and argument about two complex numbers when they're either divided or multiplied and so on. Okay, so when you have two complex numbers that are dividing, so you have z1 divided by z2. Okay, you can simply find the modulus without calculating the new complex number. So you don't need to calculate the new complex number z1 by z2. You can just do modulus of z1 divided by modulus of z2. Okay, what happens to the argument? The argument of z1 gets subtracted with argument of z2. So my purpose of showing you this is to show you that you don't really need a new complex number. You can just use your old complex numbers and do this. Similarly, when z1 is multiplied with z2, I could make it easier. Wait, in terms of writing it down, let's say two complex numbers u and w. Okay, so this would be modulus of u divided by modulus of w, and this would be argument of u minus argument of w. So z1 z2 is already written in your notebook, so you can see that happening here. Okay, then let's say two complex numbers are being multiplied. Their model will also get multiplied, and this time their arguments will get added. Okay, then if you have a power on a complex number, this becomes u power n, and this becomes n times argument of u. Okay, those are the three rules that will help you solve all the questions. Okay, where is the question on this? I will show you a question on this later on. Let's just first do this and see what it says. Okay, we have the rules in front of us, and हम जो है वो इनको solve करने की कोशिश करेंगे. I'll need my calculator. See if I have it. Yeah, I have it. Okay, so what I'm going to do is I'm going to first calculate the arguments of these two modulus of these two numbers and the argument of these two numbers. So mod of z is root of 8, and w is okay 4. Okay, then let's just focus on the mods for now. Okay, so what's the mod of z square? We just did this, that if you want to calculate the modulus of u power n. It's simply the modulus of u power n. So this is just going to be root of 8 squared. Okay, just applying this rule that I wrote down on the third step for you, that you can just take the modulus of z and square it and you would get the same answer. Similarly, z cube would be root of 8 cubed. Okay, I can use a calculator to simplify this. I know what it's going to be. It would be 8 cube root of 8, which is 2, I think. Square root of 8 power 3. It's going to be 16 root 2. That's going to be 8. Okay, for C, you need z square multiplied by w square. Okay, you already have z square, and when two complex numbers are being multiplied, their mods are also being multiplied. So this is going to be basically mod of z square into mod of w squared, and those are then modulus z squared into mod of w squared. Okay, I'm just applying the rules. This is how you would derive them. You don't necessarily need to derive them. Okay, and that's root of 4, which is 2. So 2 squared gives me 32, I think. Okay, similarly for D, I'm just doing the mods for now. I'm going to do the arguments in a bit. W squared over z cubed. So the mods are going to be divided. The mod of w squared was 4 and z cubed was 16 root 2. So that's going to be 1 over 4 root 2. You can use your calculator to rationalize this. Okay, your calculator can also calculate all of these directly. I'm going to do another calculator session to show you how complex numbers can be done directly on a calculator. Okay, let's now calculate the arguments on these. For again a, I'm doing this. I'm just going to first write down what's argument of z. Z is in the first quadrant, so it's tan inverse of 2 over 2, which is pi over 4. And where is w? W is, the real part is negative and the imaginary part is positive, so minus 1 and root 3. Okay, tan inverse of y over x, tan inverse of root 3, pi over 3. I think I changed my calculators. Pi over 3. Okay, so let's now do a. That's just argument of z square, which is 2 times argument of z. That's 2 times pi over 4, pi over 2. Okay, according to the rule. Then if I have argument of z cubed, 3 times argument of z, that's 3 times pi over 4. That's 3 pi over 4. For C, I have z square into w, when w square. So when you have argument of z square into w square, what happens is first the arguments get added, and you can calculate each of these arguments by saying 2 times argument of z plus 2 times argument of w. So 2 times pi over 4 plus 2 times pi over 3. Okay, that's certainly going to give me an answer that's greater than 180 degrees. I might have to turn that into a smaller answer, depends on the question. For now, there's no limit on the on how big or how small the argument could be, so I'm just going to let that pass by and come back to it when I do an actual question. And it's 7 pi over 6. Okay. And it's w square over z cubed, the argument of w square over z cubed. Oh, my bad, I I've made a mistake here. This argument would be this number, so it wouldn't be pi over 3. In quadrant 2, I would have the argument as pi minus pi over 3. It's 2 pi over 3. So 2 pi over 3. That's 4 pi over 3, and 4 pi over 3 plus pi over 2. 4 pi over 3 plus pi over 2. 11 pi over 6. Okay. The argument of this would mean argument of w square minus argument of z cubed. So 2 times argument of w minus 3 times argument of z. 2 times 2 pi over 3 minus 3 times pi over 4. Pi over 12. Okay, how do these questions come up then in a past paper question? You can copy them down by pausing the video. I want to show you one particular past paper question that's there, and then I'm going to solve some more past paper questions for you as well. I've already solved this one. Yeah, this is the question that I want to solve for you, and this shows how this last part will tell you why I taught you those rules right now. If this is a complex number, is this its complex conjugate is u star, so 3 plus I. On an organ diagram with origin O, show the points A, B, C representing the complex numbers u star, and u star minus u. So I will have to do u star minus u first. So that's 3 plus I minus 3 minus I. 3 plus I minus 3 plus I. 2I. So let's try to represent these on a diagram. Okay, 3 minus I, 1, 2, 3. 3 minus I and 3 plus I. So that's point O, A, B, and C. Okay, that looks like a parallelogram to me. It looks like a parallelogram. Okay, that's a parallelogram. I get full marks for doing this. Showing you're working without using a calculator, u star over u. So I think that's simple. 3 plus I over 3 minus I. To do the conjugate, to do the rationalization part, you'd have to multiply it with 3 plus I and 3 plus I. That gives you 3 square minus I square, and in the numerator it gives me 3 plus I whole square. Okay, so that's 9 plus 6I plus I square. 9 minus minus 1. So I am getting 9 minus 1 plus 6I divided by 10. So that's 0.8 plus 0.6I. Okay. Now that was part 2. That was easy. Now just by considering the argument of this, prove that. I want to prove both sides to you. Okay. So argument of u star over u. I know from my rules that argument of u star over u would be argument of u star minus argument of u. Now I already have this number, so can I write down that I'm talking about argument of 0.8 plus 0.6i into argument of basically 3 plus I minus argument of 3 minus I. What quadrant is this? This is the first quadrant. This is also the first quadrant, and this is the 3 minus I would be the negative quadrant 1 or quadrant 4 for that matter. Okay, so in quadrant 1 it's going to be simple. My alpha is going to be tan inverse of 0.6 over 0.8. Is that 3 over 4? Yeah. Okay, so my argument comes out as tan inverse of 3 over 4. For this one, the alpha is going to be tan inverse of 1 over 3. It's in quadrant 1. So this also becomes tan inverse of 1 over 3. Okay. Then there's a minus sign because there's a minus sign here. And then you have the quadrant below. So the alpha is tan inverse of 1 over 3. But the argument for the fourth quadrant is negative alpha. Okay. So I'm going to write tan inverse of 1 over 3 minus tan inverse of 1 over 3. So 2 tan inverse of 1 over 3 basically, because that's going to become a plus. So I've proved to you. Okay, this is a common question that's been repeated twice or thrice. Please make sure that you look out for these questions where they ask you to show that this is what you have to do in the question. Okay. Okay. So that was the application of what I showed you earlier. There are a few more questions that I am going to solve because I think I want to complete this exercise. It's going to take me a while to solve these 3 questions in front of you. And then I think there's another one at the top as well. This one says it is given that minus 1 plus root 5i is a root of the equation this, where a is a real number showing you're working. Find the value of a and write down the other complex numbers, complex roots of this equation. Okay. Okay. So z cubed minus 1 plus root 5i cubed. Okay, to cube the number, I think it's easier to, just multiply it first, break it up into square and then 1. So that becomes 5i squared minus 2 root 5i plus 1. Root 5i minus 1. Writing down the other complex root is easy, I think. So that gives me minus 4 minus 2 root 5i and root 5i minus 1. Let's multiply minus 4 root 5i plus 4 minus 2 root 5, 2 root 5 into 5, that's 2 into 5, I squared plus 2 root 5i minus 2 plus 2 root 5i plus a equals to 0. I think there's some things cancelling out, so this cancels that with this and that. So minus 4 and this becomes minus 10 into minus 1 will be plus 10. And minus 6 is 4, and then a is therefore minus 4. Okay, that's part 1 of the question. Part 2 says the complex number w has modulus 1 and argument 2 theta radians. Show that w minus 1 and w plus 1 equals to I times tan theta. So I want to prove to you that there's a complex number called I tan theta, which means that I must have w in the modulus argument form. What is the modulus argument form? The modulus argument form is r cos theta plus iota r sine theta. You're telling me that the modulus is 1 and the argument is 2 theta, I think. That's what the question is telling me. Yeah. The argument is 2 theta. So w equals to 1 cos 2 theta plus iota 1 sine 2 theta. So cos 2 theta and sine 2 theta I. minus 1 plus 1. Okay, so there are real parts and then imaginary parts. Again, if I need this in the numerator, I will have to rationalize this. So what I'm going to do is I'm going to multiply the denominator with cos 2 theta plus 1 is the real part. I'm going to change the imaginary part sine 2 theta I, and I'm going to multiply the denominator with that as numerator with that as well. Okay, what I'm trying to do is I'm going to try to remove the denominator, because you see what I have to prove doesn't have a denominator. Might have a denominator. I'm expecting to get sine theta in the denominator, but let's see what happens. This will become cos 2 theta plus 1 whole square minus sine 2 theta I whole square, and that also becomes I'll multiply that separately, because cos square 2 theta plus cos 2 theta plus no, that's a longer multiplication than I thought. I think there's the other way out. Sine 2 theta I cos 2 theta. Okay, then I have plus sine 2 theta cos 2 theta plus sine 2 theta I, and that is sine 2 theta I cos 2 theta I, sine 2 theta I, and plus into plus 1, and then minus sine 2 theta I, sine square 2 theta I square, and then minus cos 2 theta minus 1 plus sine 2 theta I. Okay, I see lots of things that could cancel out possibly. So this cancels out with that, and this cancels out with that. So I have cos square 2 theta plus sine 2 theta I plus sine square 2 theta, which I changed I square to minus 1, plus sine 2 theta I. Okay, and what's happening in the denominator? I have cos square 2 theta plus 2 cos 2 theta plus 1 minus sine square 2 theta I square. So I have cos square 2 theta plus sine square 2 theta. That should give me 1 minus 1 plus 2 sine 2 theta I. It's a complicated trigonometric identity. That's pretty much what it is. If you now see this, this also becomes a plus because of this. So this becomes 2 cos 2 theta plus 2. So I'm getting 2 sine 2 theta I over 2 cos 2 theta plus 2. I think the 2 is common. So get rid of that. Sine 2 theta becomes 2 sine theta cos theta, because I know I need to change it to tan, and this would leave out cos 2 theta plus 1. Actually, I've taken a common and subtracted it. Okay, then in the denominator, how do you cancel out 1? You use the identity to cos square theta minus 1. That's plus 1. So 2 sine theta cos theta. I think that is working out. Cos theta, this cancels out, then cos theta cancels out cos theta, 2 cancels out with 10, and tan theta equals to I. That is the correct solution for this. It's a long solution, but and sort of a hectic one as well. So make sure that you understand this before you go on. Okay. I just expanded and solved. I just did applying identities till I got to the very last part. Okay, let's do this one. It says throughout this question, use of calculator is not permitted. You'll probably not be able to use it either. The complex numbers w and z satisfy the equation. Given that z equals to 1 plus I, find w, giving your answer in the form x plus yi, where x and y are real numbers.
Welcome to Edge Learning, where we are changing dreams into success stories. Let's go! At Edge Learning, we offer courses to help you excel. Whether you're preparing for the SAT, aiming for IBA and LUMS, need O and Alevel tuition, or IELTS coaching, we have the right program for you. Forget about boundaries. We offer learning anywhere, anytime. Our expert tutors provide personalized attention in various batch sizes and one-on-one sessions, along with pre-exam review workshops to ensure you perform your best on test day. Join us at Edge Learning and take the first step towards turning your dreams into reality. So what are you waiting for? Register now or call us.